continuing with another talk on the Knispel on axiomatic set theory with pure elements in dynamics.
Yes.
Excellent. So yeah, please.
All right. Yeah. So this is definitely work in progress and something that I just did a few months ago, I think, maybe only 1 or 2 months ago. So this is partially sort of, I want to give you an idea of why you might want this, why this maybe works better than other approaches that I've seen so far, and also some of the problems, of course, that I have encountered along the way. So, I mean, the main question is, of course, like, why would you want? Well, maybe you can ignore the axiomatic part. Why do you want set theory? Well, you might actually be forced to use some kind of set theory sometimes, right? That's just something that happens from time to time. At least that's something that happens to me from time to time. I think it's not the third time or so that I just had to use set theory for something in the proof system. I found that often, I mean, you have sort of ways to emulate set theory. Maybe you do something like lists or trees, or maybe you have some kind of propositions or one-area properties. But all of those are sort of ad hoc and don't really necessarily give you all the axioms you would expect in set theory, and all of them are sort of slightly different. And yeah, so the idea is maybe we can take one approach to set theory that has all of those implementations as models, and then we could just build our set theory abstractly without picking a model, and whenever we then actually need a model for something, maybe because we want to compute, or maybe because we actually need to use some specific things that are only true in the model, well, then we can actually instantiate the model and go from there. But many of the common things, of course, we can just sort of do generically over the set theory. And here are sort of my reasons, most recently, why I actually did this. So we had a lot of implementation details leaking everywhere in sort of a list-based formalization of set theory, and the amounts of things that were broken and ugly that should have been easy were just too many. So lots of inference for implicit arguments that should have worked was broken. Many proofs that should have been one-liners were 10-liners or longer, and those issues really kept piling up. And so the idea was, okay, let's get rid of all of that. Let's do axiomatic set theory. This forces you to have proofs that only use the axioms, right? Which maybe in the beginning feels a little bit more difficult, but you soon realize that actually this additional constraint prevents you from doing wrong things, or things that would get you in trouble later on. Yes, so let's change the resolution. It used to look nice. Maybe, let's see. This is good. And let's hope that this keeps working. Yes, so these are the basic axioms that I'm using generally, and those are inspired by the classic ZF axioms. There are two key differences here. And the first one actually is already in the first line. So this is a record. I didn't put the line that says record. Didn't really add anything. So already in the first line, there's one key difference, which is that we do say what. Yes. So set is goes from type to type. So we have set of A, where A is the type of elements of the set, and this is if you are familiar with the set of axioms, then this is not how sets work classically. You don't have a type of elements or anything. You just put in there whatever you want, and this is one departure. And of course, I think I've seen one exception where someone in a proof system didn't do this, but it seems sensible. And it worked pretty fine so far. And this is where the UR elements come in, because this A, for example, is then the type of UR elements, because those are things that wouldn't be classically in the ZF model. Then, of course, the membership relation, and then there's this spec property. And this is the second departure from the classic ZF axiom tree. I mean, there are some other small things, but the second big one. And this spec property shows up here. And so what this is doing is the specification axiom says how can you, if you have a set and a property, then I can construct another set of elements of this original set that satisfy this property, so like a filter function. And so depending on what you're working with, you might want to restrict the properties that you allow in the specification axioms, right? So in classic set theory, you just allow anything, and in the model of sets as union properties, you would also just not put any condition here. For example, if you're doing lists, then you actually need to put the decidable here. So you need to require that your properties are decidable. And so depending on what model you actually want to fill in here, you might need to sort of put a notion of property that you allow in the specification axiom. So this then works pretty well in practice, and it doesn't generate all that much overhead, actually. So this seems to work pretty nicely. And then, yeah, just to quickly go over what these axioms do. Well, the first one, specification, we talked about. Let's just specify a subset. Unions is if you have a set of sets, then you can make a set that's the union of all of those sets. So crucially, if you have, for example, infinite sets, then this lets you do infinite unions as well. Then the replacement axiom is basically a map function, and listing is another slight departure from classic ZF, but not really, because in ZF we usually have the pairing axiom, which says that if you have two sets, then you can make a set that contains the two of them. Then I forget if you need to do something. It sort of depends. So if you have any set, so I think classically for the pairing axiom, you can actually construct the empty set, because you can take the pairing and then you can create a subset that doesn't have any of those two in it, and then you have an empty set. But this restriction with the UR elements does not necessarily give you an empty set, since if you put the bottom type there, then you can't use the pairing axiom to create anything, and then you can't get an empty set. So, I'll come back on my screen. Yeah, so this, so I would have to have an empty set axiom to get an empty set at the bottom type. On any other type, I could do it because of listing, because of pairing, but at the bottom type, I would have to have a special axiom, and that's all kind of annoying, so I just put a list in here. Yes?
So set membership is not a proposition in this framework?
Ah, yes, I should. Wait, set membership is a field that we.
I mean, in the what sense, like the age level of being a member of a set. Like, if this is equivalent to being in a list, then there are different ways of being a member in a set, right?
Ah, okay. So that's true. I haven't cared much about how, sort of, if you have different proofs of things, like how that would influence anything. So these equivalences here are just functions going both ways. So I don't require that they compose to the identity. Maybe maybe that would make sense to require something like that in the future. I haven't really given it much thought. Yeah. Okay. And then so
also your elemental is not between sets, but just between a core element and
yes. Yeah.
So it's more like a collection, like a classical computer science structure collection, rather than this mathematical set.
Well, so since we can, of course, have, for example, here sets of sets, we can still sort of have arbitrary deeply nested layers of the sets. So this.
Yeah, but it's stratified, right?
Yes.
Because it shows in the type. So.
Yeah, yeah. Yeah, I mean, that's kind of, I guess, a consequence of this first departure that we have the type of elements. Yeah. I found that it works pretty well, and it behaves pretty well too. So.
Do you need undecidable membership?
So membership can be undecidable, but that sort of depends on a bunch of things. It depends on this spec property, and it also depends on the base type. Right? If equality on the base type is undecidable, for example, well then I can't have decidable membership. And if the spec property is also not decidable, then I can only have decidability if I know already what set I have. But if I have decidable equality on my type, and if the spec property is decidable, then membership is decidable. All right, so then, yeah, so there are maybe 3 axioms that are missing that people might expect. I left out the power set because I didn't need it for anything right now, and it's difficult to prove. But of course, that's easy to state. I don't have an axiom of infinity, which is, I guess, always part of classical setup, because I want to allow for lists to be a model, and so I can't have an axiom of infinity. But of course, you can always make an extension of this, because the record and module system like that kind of works pretty neat. So adding an axiom here is pretty easy, and you're just re-exporting everything. So this is pretty nice. And then of course I have a choice. So yeah, in my list model, for example, I do also have the theorem that every set is finite. And so I also, for example, have a version of these axioms where then I say, well, it's supposed to be a finite set theory where every set is finite. Because sometimes actually constructing a finiteness proof is difficult, but if you know that your set theory is finite, then you don't have to do anything, just get it for free. I think I talked about that pretty much already. Yeah, so exactly. We have this problem that sort of decidable or any property, both of them are useful in some cases, so we would like the ability to just pick whatever you want. Right, and so then what can we do? And I just picked a bunch of random examples that I guess people are familiar with. Usually, so for example, what does finiteness mean? There's actually two different versions of finiteness. Because, so what I'm saying here is, I call a set finite if there's a list, so that the elements are precise in the list are precisely the elements of the set. But of course, I could also just have the implication that the list has all the elements of the set, but not necessarily the implication in the other direction. Obviously, there's other ways of doing finiteness. This is just convenient and easy to state. So the other version, where you only have one direction, is called weakly finite, and of course they are not equivalent in general. And so often finiteness is very useful, but the problem is if you have a subset of a finite set, then you don't necessarily know it's finite when it's weakly finite. So there are some interesting problems here. Then, for example, we can just define finite sets. Pretty obvious. Relations are classically in math just sets of pairs, and we can then, for example, say we have left unique relations, where if you have two pairs that have the same element on the left in this relation, then their right-hand sets also agree, and those are of course partial functions or maps, and so that's actually something that I'm working with a lot. And yeah, so those behave a lot more like the notions of relation sets and so on that you have in math, because you can do all the classic set operations with them. You can combine a bunch of things together and then prove that it's a function that what you've constructed, for example. So that might not be what people in this room think is nice, but that's nice for me sometimes, yes.
So these are external maps, right? Can you actually get a set of functions from A to B?
A set of functions from A to B.
Because you said there are not functions.
This should work. I can make a set of all. So there's one issue, which is that the axioms don't necessarily imply that if I have a type A, that I have a set of all elements or of all members of A. And this is of course false in some models. But if you have that, if you have a model where this is true, then you should be able to construct the set of all functions, for example, because you can then start with the set of all relations, which you know exists, and then just use the specification axiom to select a subset.
Right, but I don't think this is true in any model, right? So there will be a paradox in any type into a set. Right? Set and set.
Why would this be a paradox?
Because the type of all sets is a type, but it's not the set.
Universe levels. I think I would have to look at this later, but I think this should work if you have an axiom that gives you for each type a set that contains all the elements of that type.
Yeah,
I think
that's the axiom I doubt is true, and I know.
well, it's true in the model where you have like the functions from A to Z as so yes, there are some problems with level polymorphism here, but what you can do is take functions from, I think, from type 1. So you take a type 1 and map that to, call it A, and you then take functions from A to type. That I think should still be a type 1. And then I think you can make a model of set theory that has that property. But I haven't tried that yet. So I think this should be. I saw you first. Probably should have disabled my screen mode. Nice.
So the axiom I didn't see, or non-derivable, is idempotent. Like, if A means A, is that equal to A or not? And I didn't see that. So basically, do you have set or do you have multi-set? Which are, like, at the level of axiomatization, kind of hard to tell apart.
So I have, I don't think I've mentioned quality here. So I guess this would be the next slide below here, where I define equality, and equality I just define as extension of quality.
You don't need equality in multi-perspective for differentiating. Like you just need idempotence. Or you need set minus or something.
Yeah, so
basically I think I'm saying that multi-sets are a model of this.
yes, I think so. Yeah. So I do have extension equality that I use for many things that need equality. And then of course you don't see the difference anymore. But I mean since lists are a model, yeah, I mean of course multisets will be too. Yeah.
So I have a question in this slide and one in the next one. So is that exists or is that sigma?
It's
Anyone know how much time I have?
Well, you stand between us and lunch. So.
Yeah.
actually we'll have a discussion, but
I think the discussion is going to have to be left for after lunch.
If that's still all right with you.
Yeah, we should have discussed it already.
Yeah. Good.
Only
Okay,
for
then indeed, so let's leave the discussion for after lunch, and let's finish the talk first, and then.
I mean, I think I only have 2 more slides after that.
We have some amount of time, use it wisely.
Yes.
Some of us are very, very heavy chargers.
Okay.
Anything else, legend
Right. So there was a question I remember just now.
Right.
I already answered a bunch of questions outside, but there was a question. I think what is this, right? That was
Yeah. Are those existentials or are they sigmas? Like, are they truncated or not? Put it like that.
They are whatever is an extended library and it's called.
Okay. So
I think it's a sigma.
Yeah.
So yeah. I think it would be definitely interesting to think about implications for like cubical. All of this is of course without k. I think there are some. I think when decidability comes in certain cases, then I need k for something. But most of it, definitely the axiom itself and most proofs are without k.
Yeah.
At least. And of course safe, obviously. Right. So yeah, I was talking about how we can do sort of classic set operations on those things to, for example, build a function from some parts and then prove it's a function, which I think is nice and I actually need.
I also want to point out that that is the type of partial maps from A to B.
Yes.
So the empty relation is a map from any type.
Yes. Yeah, that's intended here. I also have a like another one where there's also an additional constraint that it's supposed to be total.
Right.
Yeah. So yeah, this is this is the like map in programming languages.
Okay.
So, and this is what I use most of the time in my work. But there are also some places soon, I think, where we actually have to have like total maps or functions. Right. So one thing to that is very interesting to point out here is how do we then go about computing things from those sets. So one application that I have is I have a set that maybe I want to the elements of the set are in maybe some monoid or group or whatever, and I just want to take the sum of all of them. And so this is kind of a shortcut. You can see here this equivalence. So this is actually in a satellite. You can ignore that for now. So here, so I define this factor function, and the fin set, of course, has is a set together with the proof of its finiteness, and the finiteness proof consists of a list and the proof that the elements are the same. And of course, here I just project out the list, and then I can apply the function. This fcom at the top here basically says, well, if I have two lists that have the same elements, then my function better respect this in the appropriate satellite equivalence here. And then I will have actually a well-defined function on my sets in the quotient, and then yeah, this factor common, for example, is then the proof that it's actually well-defined, and you can of course get a few more properties out of this factoring. But it turns out that this is very difficult to use, because if you actually write a function, if you take the sum, for example, we have exactly this problem with multisets, where maybe if you mention something twice, well then the sum for lists will just add it twice, and then you have too much things. So you would probably like to not run into this problem, where you can actually define a function without having to filter out duplicates or something. And so this is this factor unique. So I have a module that basically re-exports those things except different arguments. And so here I'm saying, well, I just take a list that doesn't have duplicates, and only for those lists I need to define a function. And on those I can just sum all the elements, and it's fine. And then my congruence changes slightly, and this, if you're not familiar with the standard library, it is that the two lists are permutations of each other. And so then you have to do things for permutations, but only have to provide a function on unique lists, and then you can define your function that sums over everything. And this also requires the silent point. Forget exactly why that was, but it does require it somewhere. Right, and so what are some problems with this? And so we already talked about the universe question. I have generalized this over some. So I made the type of the definition set to be from like type L to type L. So and that all works out pretty fine. But the problem is if you want some model, for example, like properties, then we have this issue that we need to keep the level the same. And so I think this works if A is of type 1. But yeah, it's kind of annoying that it doesn't work if A is a type level 0. So yeah. I don't know what,
but yeah, why does setting fill up the level?
Yes, good question. I can. So this might be actually something to be relaxed, but the union axiom takes set of set, and that of course only works in good cases. That's the same problem why monads, for example, need to preserve the level as well. So, yeah. And of course, if you try to instead make it polymorphic over the level and then just accept everything, then you run into other, like that. I think this doesn't work. Or maybe you run into other problems. I don't remember, but there are definitely other problems. So, yeah, levels are definitely one of the veins of long distance. Right, so then spec property. The question is, what should this be? I already talked about this a little bit outside, but spec property is currently just some restriction, like some class of properties that is preserved under negation, and you can pre-compose with functions, which isn't maybe all that much. This works so far for everything that I use, but of course, this might easily break. And so one option would just be to sort of extend this and add more and more preservation laws, but of course, this doesn't maybe scale the way you want. And so another option would be to just say, well, we could say, I just give you two options, decidable or any property. And then you could go and prove the preservation that you need for decidable properties. And if you don't restrict the class, then of course you don't need to prove anything. And then you could sort of add your own things that this spec property sort of preserve. But I don't have a need for it yet. But that's one of the areas in the design space where it's sort of open what exactly to do. So that sort of depends on maybe if other people have other use cases, then maybe it narrows down the design space in some useful way, but I didn't have any of that yet. Right, and then there are a few things where things are a bit difficult to use. So for example, finite set is of course a set, right? And so if I take the union of those two, well then ideally I would just not have to project out the set from the pair to take the union. I would just like to take the union. And then since that's finite again, well then maybe I want to also have to prove that this new set I've constructed is again finite. But the problem is that finiteness is actually relevant, right? Because in this factor function, for example, we actually compute on this list. So we can't just use irrelevant instance search to fill in those problems with whatever. So I'm not entirely sure yet what's the best way to go about this. I've used instances a little bit to try and make this easier. But it doesn't always work, since, for example, if you have a proof that every set is finite, then the instance search will get stuck because it'll have a proof that every set is finite, and it'll also have a proof that the union of finite sets is finite and doesn't know which one to use, and I don't care. Just whatever. So that's a bit problematic. For other properties, I think finiteness is really the only property, at least that I have encountered so far, that is relevant. So for other properties, I guess the instance approach would work quite nicely. I don't really, but finiteness is also the one that I encounter the most. So, right, and then the last line in ergonomics is so Lean has this nice feature where you can overload type annotations and function applications. For example, you can say I just want to if I have a ring or something, and I put that as the type of something, then it would project out the carrier of that ring. And that's, of course, it works kind of like the literal overloading that we already have in Active, where you could then give a type class that does this cast for you. And that's exactly how Lean does it. And this works pretty well for them. And the same thing for applications where the left-hand side you could cast to a function type. And this would be very useful to sort of clean up the notation of this a little bit. And then finally, tactics. So here at the bottom, this any of will just try any of those names to solve the goal. And this is pretty neat because this will do introductions or eliminations for membership, right? So if you have, for example, A in union of X and Y, then this tactic will automatically, correct methods, will automatically give you that A is in X or A is in Y. And similarly for other things, of course. And this is pretty convenient. Should come back in a second. The problem with this is that I have to literally copy and paste this into every file where I want to use it. Because, so there's this issue, I think it's a couple of years old, about hygiene in macros with module, like with parameterized modules. And if I try to import those macros from another file, then my De Bruijn indices won't be right. And so then I have to copy and paste this everywhere. But it's very nice to use, so the pain of copy pasting it everywhere, I'm willing to pay that. But yeah, I think we talked about this yesterday a little bit at lunch, where maybe we can make a macro that defines this instead for you.
No. It's my suggestion.
Quote a macro? No, no way.
No, just, yeah. Just have a macro that generates a macro for you. I think you can already do it.
Yeah, and but
maybe using a quote that.
But I find this works quite nicely for sort of working with expressions of sets to transform them into logical expressions, prove something about them, transform them back, and then we have proved that two sets are equal, for example, or that they are subsets of each other, or whatever. And so this is probably the nicest or the most necessary tactic, because if you then repeatedly apply that, of course you can actually get it to do a bunch of work for you. I don't have intersection here yet. I should probably add intersection and maybe some other properties. Yeah, and I think that's all.
Questions, okay?
Yeah.
Yes, of course.
One question is, are you aware of Volcom Filter's work? And I think Elizabeth Olivier, they're doing like set theory and homotopy type theory. I think they eventually want to go towards like non-well-defined set theory because they're interested. But if you're not, this is kind of interesting because it's also done in ACT. You could maybe steal some ideas.
Interesting. Yeah.
Like they do it in, I guess, Kubernetes, because, well.
No, it's I think it's a Martin's type topology paper.
Oh, okay.
Well,
Well,
the univalent stuff is just assumed as module parameter.
well, okay, that's. But in the end, like it's like homotopy type theory, but I guess you don't really need to know that much about homotopy type theory to understand what's going on. Yeah.
That's interesting. Yeah, so
I can post a link to that. I guess.
yeah, I haven't heard of that. I think a year ago I searched for set theory formalizations in ACT, and I think I found 3 or so options. And all of them, well, I used one of them temporarily, but I got, like, the pain got too big and then I had to do this.
Yeah, you mentioned at the beginning that you saw one formalization which didn't take the approach of having macro elements. How will this work? How can this work?
So, well, you just don't do it, right? So you would say you have a type of sets, and then your membership relation relates to sets to each other, and then like you never have set of A, you just have a set, And so there's this, it's, I think some Japanese, or at least it sounds Japanese, the name of the person who did it.
I mean, how do you have any elements in the set? Like the issue is really foundational, right? In type theory, you kind of don't have, like you don't assume that there's some universal things, you just construct everything.
So here, I mean, I have this listing axiom, right? And that doesn't work classically because you don't, as you said, you don't have that if we don't have these full resonance. But this pairing axiom would then basically say, would say, if I have two sets, then I can put them together in, then there is a set that contains those two sets. And that's an axiom. And then of course, how do you get those two sets? Well, for like one way of going about that is, so classically there's an axiom that, I mentioned this here, there's an axiom that there exists an infinite set. And then you have one set, and you know that kind of bootstraps everything. Of course, you could also, another option would be to have an axiom of an empty set, for example. Then you can bootstrap everything that way. So classically, like in classical mathematics, if you read a book about set theory, then you quickly realize that sets are just parentheses around empty sets, basically, in the if you don't pick a model. And you can do that here, right? Because you can start with the empty set, and then you can make a set that contains, because of the listing axiom, you can then make a list of a bunch of sets, and then there will also be a set that contains those things. And so you can also start with an empty set and just put parentheses around that in here. So you have all those sets that you have classically, except that you have this stratification here. You have to say like how many parentheses are allowed, basically. And then you can make it, for example, at the bottom type to forbid any actual or elements, or you can also allow them if you want.
Okay, let's thank the speaker. Thank you.